We're really happy to have Dr. Emma Spooner with us. She's from the University of Manchester and she'll be kicking off this session. And she'll be telling us about what I think is very interesting, and that is scalable, semi-transparent organic photovoltaics, which I think can also be printed. And this is a joint work between the University of Manchester and also the company Contra Vision, if I understood it right. So I think Dr. Spooner is going to present first, and then after her, we'll hear from Francesca from Rebus Tech, and finally we go to Canada, where we'll hear from the Brilliant Matter team. I think Felipe is going to join and present on their behalf. So without any further delay, the stage is yours.
Okay, so hi everyone. I'm Emma. As Kasia said, I'm from the University of Manchester, and I'm going to talk to you a little bit about the project I'm working on now as a postdoc. So I think that we all know what OPVs are, but just a reminder about why people still care about them. So obviously their efficiencies lag behind that of perovskites, but they still hold some kind of unique advantages, especially in terms of tunable transmission. So this is great for things like semi-transparent solar. It's great for things like agrivoltaics, and really just from kind of careful molecular structure tuning, you can do this with a lot of fine control. So this is a really exciting area for OPVs, and where I think that they will continue to grow. I thought I'd maybe briefly describe how do you make a semi-transparent OPV, because I think sometimes it's not always clear to someone new to the area. So the really high efficiency OPVs, the record ones at the moment, are using non-Fullerian acceptors. They're using Y-class acceptors most of the time, and these absorb very strongly in the infrared region. So this doesn't impact our visible transmission very much. We can leave this where it is. In contrast, the donors, our best donors, absorb quite strongly in the visible regime. So if we want an OPV that's transparent in the visible regime, then this is what we need to modify. So the most classic strategies are either using redshifted donors. So if you see in the top right, this is an example of a redshifted donor where someone has modified PM6 to form something called PM2, and this is absorbing quite strongly in the infrared. And you can see the human eye response they've put there, which is sometimes also called the photopic response of the eye. These are the wavelengths that the eye can see. So these are the wavelengths that really matter for visible transmission, for example, for something like a window. You can also use dilute donor systems. So this simply means reducing the weight content of your donor within your bulk heterojunction. So you can even use just a classic PM6Y6 system for this. And at the bottom right, I've shown this, that if you go down to something like 10% weight content, compared to the traditional weight content, which would be about 40 or 45%, you can really improve your ABT. I think generally if you get below 10%, you start to see non-functional cells. So something around 10% is kind of a great balance between performance and transparency. What's also commonly used are optical layers. So Steve Forrest in Michigan is a big proponent of these, which is where these figures are from. So anti-reflective coatings are popular and have been for a long time. This is something like lithium fluoride, but you can also get a bit more complicated with it, stuff like dielectric Bragg reflectors or outcoupling layers, which will do various things related to visible transmission. So outcoupling layers are good for achieving a neutral color, whereas distributed Bragg reflectors are good for reflecting near-infrared photons, etc. So if you're willing to delve into the more complicated structures, then you can do quite a lot of interesting things with the light. So people use some terms specific to semi-transparent OPVs that I thought were worth mentioning. So average visible transmission, sometimes people will just integrate over their whole transmission spectrum and call it ABT, but that's not really technically what we should be doing. So the window industry actually use this definition where your transmission is weighted against V, which is the photopic response of the eye, which is what I mentioned earlier, and AM 1.5. So that's the definition I'll be using throughout. And there's a bit of a push in the semi-transparent OPV world for this to be adapted by everyone as the definition of ABT. Using your ABT definition, if you times it by PCE, you can get your light utilization efficiency. So the record semi-transparent OPVs, and I think it's actually pretty similar for semi-transparent perovskites, light utilization efficiency is around 5. So this is, for example, a 50% ABT cell